Thank you. So I'm going to try to do an interactive talk. So if you have an Android device, you can download this app. There is no... This is a legit app. It is not... It's just an app that is not available on a Play Store anymore. So this is why I've... Okay? And okay, so first, so I'm going to talk to you about ultrasounds and how they can be used to track you basically in the physical world. So this is not something that I have discovered, but I have focused on one specific application. And with my colleague Leonardo Cardoso, we managed to reverse engineer this application, and we try to understand how it works. So if you haven't downloaded, you can still do it. So ultrasound can be used as a side channel. So there are two recent works published in 2015 that investigated how ultrasounds can be used to perform some malicious things. So the first case is media tracking. So basically, ultrasound signals are injected inside videos, radio broadcast programs, and when you have a device that can listen to those sounds, it can recognize signal embedded in those medias and recognize what TV show you are watching. This is the first application. You can also have the second case where you have a signal that is broadcasted by one device, and then you have another device that is sitting next to it that will receive this signal. So you can, from that, deduce that the two signals, the two devices are located in the same room. You can do many other things, including location tracking that I will talk about it later. You can also re-identify people that are on tour. For instance, if you are visiting a website on tour, and if this website embeds some ultrasonic beacon signal that is generated, and if you have your phone next to it, and if it happens that your phone is listening to the sound, then it will be, an attacker could be able to re-identify you. So I'm talking now about beacons. So maybe you've heard about those things called iBeacons, Eddystone. Those are Bluetooth beacons that are installed inside shops, shopping centers, and they are basically broadcasting a unique identifier. So this is done in Bluetooth. So we know how it works. But actually, the same principle can be used using ultrasonic signals. So we focused on a specific system. So there are many of them. There is one called Spot Install that is developed by one company called FeedsUp. And it is used to obtain, for an application, to obtain the position of a user. It's based on ultrasound. And basically what they do is they provide some library that you can include in your device, in your application, and this library will be able to pinpoint the location of the user. Why I've chosen this application and this company? Because FeedsUp, they are French. They do some things that are, I believe, borderline. So several times they have been, so they are in the business of tracking and profiling people using mobile devices, and not only profiling them with their online activities, but with their physical activities. They basically want to know which shop you visited, which products you didn't bought in the past, and then they can push some ads on your device to trigger some needs from you. And they are also have been warned by the CNIL. So in 2016, they wanted to install Wi-Fi sniffers in Paris with GCDeco, and the CNIL said no. And more recently, they were, I think this is, this year, again, FeedsUp and another company who were doing basically tracking on mobile. They were not doing nice things according to the recent GDPR, the new regulation on data protection. So the CNIL say, okay, you better fix that soon, otherwise you will have some issues. So they fixed their issue, and the funny thing that a couple of months ago, feeds up was saying, okay, we are GDPR compliant now, this is official. I guess it was not really the case. So feeds up. I don't like them much, you can see. And I'll start the interactive part. So I have a video, it's not my video. This is a video provided by feeds up. So I'm gonna play this video. So if you have downloaded the app, you can turn on the app and you should be able to see some things happening on the app while the video is playing. Because this video is not only a video, there is also an ultrasonic signal that is embedded inside. So let's try to do that.
Si Léa, en pleine séance de shopping, comme 33 000 personnes en France, elle a son smartphone avec elle. Elle entre dans une boutique et elle reçoit un message. Aujourd'hui est un jour spécial dans ce magasin. Dans ce rayon, elle reçoit une promotion ciblée qui l'attire vers une très jolie robe. L'offre est exclusive et la robe lui plaît beaucoup. Elle est séduite. Elle dispose de tous ses avantages sur son smartphone au bon endroit et au bon moment. En plus, elle obtient sa promotion immédiatement. Tout cela grâce à Spot in Store et sa technologie unique de géofencing. Créer du contenu riche qui touchera votre clientèle.
Okay, I'm going to stop that. So basically the idea here is that what happened is that Leah had in her pocket, he had a smartphone with an app running on it. This app was listening to the audio signal in the shop. And in the shop, you have beacons that are installed, and those beacons, they broadcast ultrasonic signals with a specific identifiers. And when the mobile application, they take one of these signals, they can push some notifications. Okay, this is a nice robe. Oh, okay, look at those shoes. They are very nice. You can have a discount on them. And this is what happened. So their system works as follows. So, like I said, you have an ultrasonic beacon that is broadcasting a signal. Then this signal is received by an app running on the smartphone. This app needs to have the microphone permission. On the app, there is a process running. This process will perform some decoding of the audio signal. From this decoding, the application will retrieve an identifier, and this identifier can be resolved to a location. Okay, this is pretty simple. So we try to investigate. We want how this system was working, and if we would be able to play around with it. So we had several resources to start our investigation. So we had 3 mobile applications. The one that Leah used, the one that I asked you to download, the first one. A second one that is mainly used for test. And the last one, I will talk about it later. This is an application that is used in production that embed this kind of system. And last, we had also this video, and this video is really nice because it includes a very clean signal that is compatible with this system. So, the first thing we did is that we took this video and extracted the audio signal. And this is what you have. So this is a spectrogram of this video. So you have here the frequencies and here the time. And here you can see the usual things that are going in the low frequencies. But here around 19 kilohertz, you can see that you have something happening, okay? You have some peaks of signal. And if you zoom in around this 19 kilohertz, you can see this kind of things. Okay, this is not random noise that is included. This is actually a signal that is modulated and injected in the video. This is a pretty simple modulation. There's no rocket science here. You can guess that this is an on-off keying modulation. Basically, when you have a pulse, you have a 1. When you have no pulse, it's a 0. Okay? So this is, the simplest modulation that you can imagine. When you look at that, you can see 2 things. The carrier, so the frequency at which we need to search for this signal, and also the duration of those pulses, the duration of the symbols. So 2 things that are a good start if you want to understand this system. Okay, we had a pretty good idea on how the thing was modulated, but at first it was a bit complicated to understand what was the format of the signal, what was the length of the signal, if there were some headers in those packets, what were they actually packets? So hopefully we managed to find a way. We used the apps I presented and we decompiled them. And after that, we were able, by searching in all the packages, we found a couple of interesting things. So in this specific package that has a very explicit name, so Spot Install Audio Analyzer, this is where the magic happens, we found a number of attributes that are very interesting. The first one is a frequency, 19,000. So this is the frequency of the carrier. We had also a sampling rate, the pulse duration, pulse ratio, and signal size 32. So all those elements were able, thanks to those elements, we were able to fill the missing gaps in our reverse engineering. But we found out that there was another piece of information that was interesting, that we also found the presence of a CRC integrity check. So this is just a mechanism that is used to control the integrity of a frame that is transmitted. You have many CRCs that you can build. And if you don't know which CRC you are dealing with, this can be a bit complicated. Hopefully, here we had all the details of the CRCs. So in the end, it was just a matter of using those parameters to reproduce the CRCs. So in the end, what we found is that using, in this system, the information is transmitted in frames. So those frames, they are 32 bits long. So you have at the beginning one preamble of 8 bits. So a preamble is just a fixed sequence that is used by the receiver to recognize when a new frame is starting. So basically here it's just a sequence of 0 and 1s. I think it's 0, 1, 0, 1, 0, 1, that is repeated. And when you see that, the receiver says, okay, a new frame is starting, so I can start to decode. Then you have a 16-bit identifier. So this is the identifier that is used by the application to link with a location or something else. And at the end, you have this CRC on 8 bits. So this CRC includes, works, I don't think it works on the preamble, but it used to verify the integrity of the zone code that is decoded. So if the CRC is wrong, you could get, without the CRC, you could get a zone code that is incorrect, which could be bad for the application. So we have now this format. We wanted to investigate the second app I was talking about, this La Vache Noire app, because so La Vache Noire is basically a shopping center around Paris, and they are one of the first customers of this system. So they install the system in the vicinity of the shopping center, and it uses ultrasound to detect that you are inside the shopping center and where you are exactly. So if you look at the permission of this application, you can see that this application, of course, requires the microphone in order to record the audio signals and to extract the ultrasound. But you don't see anywhere the localization permission. So by using the ultrasonic channel, this application is capable of determining that you are inside this shopping center. So this application is capable of getting your location, and yet it does not ask for your explicit permission for the location. So this kind of application that are using side channels to get your location, the editors can be in quite a lot of trouble. So in the US, there is an editor that has been fined around $1 million dollars, because they were using Wi-Fi as a side channel to locate people. So this was okay, but they were also locating children. This was not okay. So, and in France and in Europe, I mean, this kind of thing should not be acceptable. So we also asked someone who was on site to collect ultrasound, the audio signal, and so he traveled around the shopping center and recorded the audio, and we confirmed that in this shopping center there is indeed signal broadcasted through, basically, there is no additional hardware. They are just injecting the signal in the audio system of the shopping center. So there is basically no extra cost for the shopping center by using that. Okay? So this is a big privacy concern, because here you see that this kind of side channel, it can be ultrasound or Wi-Fi or Bluetooth, whatever. There are companies that are basically collecting information on users by exploiting this kind of tricks, and this is not okay. And this is one of the reasons we are doing this research, is to demonstrate that some companies are doing that. And we often send anonymous mail to the CNIL, or sometimes they react, and it's fun to watch. So now we know how this system is working, and the next step is obviously to try to generate our own signals. So we know basically the frame format, the modulation, the frequency that is used. So let's try to do that. But how to generate ultrasonic signals? I'm not an expert in signal processing. My colleague Leonardo is an expert, actually, so this is why we managed to do that. But what kind of software do you want to use? Actually, there is one software that is really cool. I don't know if you know it. It's called GNU-Radio. So this is a framework, an open source framework that is used to generate, to manipulate, to process radio signal, either to receive or to emit radio signal. But we are not dealing with radio, we are dealing with ultrasound. But in the end, in fact, this is not very different. The medium that is used is one side the air, the other side the electromagnetic waves. But in the end, they are working the same way. The modulation, all the signal processing behind is pretty much the same. So this is what we've done. We've used GNU-Radio to work with ultrasound. So GNU-Radio without any radio. And this is what GNU-Radio looks like. So this is one aspect of GNU-Radio. This is a block-oriented programming language. So this is a GNU-Radio companion. So if you are not very good at programming, you can use this kind of block. And most of the time, this is sufficient. So I'm going to present you a couple of things. So here you have those boxes. You probably won't see well, but these are variables. So here you define the sample rate, the carrier that will be working. Here we have a signal source, so basically generating a signal at the frequency of the carrier, so with sinusoid around 19 kilohertz. And here we will generate our signal. So we have a source vector. This is just a sequence of zeros and ones that corresponds to a valid frame in the context of the feeds-up system. And this vector, we repeat each symbol. So each zero and each one, we repeat it a certain amount of time in order to have the correct duration. So this is corresponding to the duration of the symbol. We do that, and then we multiply this sequence of zeros and ones with the signal. We do the multiplication, so we should have something that is looking nice. And to clean the thing, we put that through bandpass filter to clean all the imperfection around the signal. And then we copy that and send it to an audio sync, so basically to the speaker of my computer. And we can also have waterfall and time sync to display the information. So this is very simple to do in GNU-Radio. This is what we've done. And again, I'm going to try to show you how it works. So if you have the application, you can turn it off and then on again, because it does not react very well to the signal I'm sending. So this is our code. I'm going to start it. So I'm going to launch the application on my device too. So I'm launching the application. So this, at some point, it should react. So I'm generating the signal. So you can see here on the waterfall, you see the signal around 19 megahertz that is sent. And here you can see at some point you have no signal, and at some point you have signal. This is just the modulation, the on-off keying modulation that is happening. So normally, my application should react. You should have some coupons. So basically the same information that is displayed by during when you watch the video. This is the same signal that I'm broadcasting here. Okay. I don't know if some of you managed to get the signal. This is a bit, no? Yeah, you got it? It's working? Great. Okay. So now we are able to generate our own signals. This is first step. So this is a valid signal. This is a valid signal, but so we can do two things basically. The first thing I haven't talked about is jamming. So we are not happy about this tracking, so you would like to protect yourself against this kind of tracking and protect the others. Or just mess around with their system because you don't think what they are doing is nice. So what you do is you take the same, the signal generator that I've created, and instead of generating a valid signal, you just use a random sequence of bits. And you send this random sequence of bits, and at the end, you basically override the real signal if you emit loud enough. And so any device that is listening to the ultrasound beacon will not be able to work because you are basically jamming this channel. You can also do signal proofing like we've done. So you generate a signal for arbitrary code. So this can be used for kind of denial of service. You can make sure that the phone of people is vibrating because they have pop-up notification. But if those beacons, they are used, for instance, to generate some coupons, if you visit my store at least once a week, I will get you a 50% coupon for your next visit. So all that, you could trick the system by generating those signal without having to visit the system and just generating the signal at your place. Okay? So this generator is available on my GitHub. So if you want to download it, you just need to download GreRadio, and you don't need any extra hardware. It's pretty simple to use. Now, to conclude, I would like to remind that this system is not the only one active around. There are many systems that have been identified by other researchers, and we are currently in the process of designing techniques that will crawl the application store in order to detect automatically new application and also new libraries, new systems that might pop up in the ecosystem. And I'm also interested in identifying a new system. So Spot in Store, I know where it is working and where it is not. And since I've started to work on this system, I'm always carrying with myself a spectrometer for audio signals. And I've noticed that in several locations, there are signals, ultrasonic signals that are generated. For instance, in the shopping center at Lyon-Pardieu, you have signals like that. At Lyon Airport, Carrefour L'Île d'Abo, but I've also seen, I invite you to download, I'm going to tell you which app you need, but I invite you to download these kind of apps, and sometime you just turn them on and you look what kind of signals are going around in the air, and you will be surprised by how many places you have this kind of signal. So I'm still trying to understand how they work. I think we are close to understanding the purpose, but we need to find also the corresponding application. This is not there yet, but I have a good hope that next year we will manage to find many new systems that are active in France. Also, if you want to defend yourself, like I said, one first way to do it is to detect ultrasonic signals. So you can download this app. It's called Spectrometer on the Play Store. This is one of the first. And if you turn your app on, and if you look at the interface, when you have an ultrasonic signal, you will see a line like that. This is pretty obvious. When you have an ultrasonic signal, you cannot confuse it with some random noise. So this is a good thing for you if you want to understand spectroid. If you want to understand and to discover a new tracking system in your environment. Also, you may want to collect all your signals. So once you've identified that there is an ultrasonic signal emitted in one specific location, you might want to record it to analyze it later. So you can use any application. I use one called Audio Recorder, but I'm sure there are many others. And also I invite you to share your samples with the community, to send them myself, so we can try to find out if this is a signal that is belonging to a system that is already known, or if it is a new system. Okay, those are the two papers I've talked about that present the privacy issues about those ultrasonic side channel. And yeah, if you want to discuss and share some ideas about that or anything, feel free to get in touch. Thank you.
So we got time for a couple of questions.
Thank you for the presentation. I imagine that the ID that is broadcast in the audio samples is used to make a request to some kind of API server. Did you take a look at that?
Yeah, we looked at one application that was doing the lookup. So we identified one ID. So the second app I haven't talked about, it was just a test application. It was detecting the signal and then requesting to get more info on the signal. So we brute force basically the thing. No luck. There was only one signal that was registered at this point. So maybe their service was not working very well. But actually, I think there are two ways of using this identifier. Either you contact an API to request more info on this identifier, or locally in your app, you already have database that contain information associated. I think in the app that I've used for the demo, this code is used to trigger a sequence of events without contacting anything.
Any other question? All right, good. We are on time. We're going to thank Mathieu again.